everyone, Mr. Geyser here with the first video in our Lesson 14A series where we'll be taking a look at logarithmic functions in context and data modeling. For these videos here, we have 6 main skills and learning objectives to go through. First, we want to write a logarithmic function when we're given 2 ordered pairs or a proportion and some real zero. 2, we want to use logarithmic functions to model proportional growth. 3, we want to use transformations based on the characteristics of the context or the data set to model logarithmic behavior. 3, we want to use logarithmic regressions and technology when given a data set to find those residuals and those different plot points. 5, we want to use the natural log function to model natural phenomena such as decays as radioactive, or when it comes to growths, or when it comes to insurance or saving accounts, anything along those lines. And 6, we want to use logarithmic models to predict values for dependent variables. In this first example here, we're going to look at a few key features when it comes to using 2 ordered pairs to find different missing variables in one of these functions here. Exponential and logarithmic functions are used to model many real-world phenomena, such as magnitudes of earthquakes, pH level of chemicals, noise levels, and radioactive decay, and many more things. For a given set of data, if the input values appear to change proportionally, meaning they go increasing at a multiple rate, times 10, again and again, times 2, again and again, proportionally over an equal length output variable intervals, then the logarithmic model can be used. A logarithmic function model has the following forms where a and b are some known constants and b is not equal to 0. Because if b was equal to 0, the log and natural log would just also become 0. For these two here, the only difference is that c would be given to us as a base for that log there. Constructing a model without technology first. In this here, in example 1, a logarithmic function L contains the input and output pairs 2, 2 and 8, 12, where L of x is equal to 5 times log base b of x plus d. In part A, we want to write 2 equations that can be used to find the values of b and d. In this case here, notice that we're given 1 point here, and we're given 2 points here. And these points here are made up of x's and y's. These here are the foundation of these 2 equations we're going to use to find these missing variables. What I mean to say is, all we're doing is plugging these 2 points into our known equation, x where x goes, and y where L of x goes, or where y goes. For A, we're going to use these 2 equations to, in part B, find the values of b and d. Notice how this equation here equals 2, and this equation here equals 12. Well, if I subtract 2 for that top one from both sides, that equation would be 5 times log base b of 2 plus d minus 2. If I subtract 12 for this one here, it'd say minus 12 at the end of here. Then both of these equations would equal 0. What I mean to say is if I subtract that front number on both sides, both these equations equal 0, or they both equal the same thing. And to make it just a little bit more compact, I'm actually going to move that front number of 5 into the log function here, just to make it a little bit easier. If you don't want to solve it that way, you don't have to. This is one of 3 different ways you could solve it. I just want to show you my way on how I'm solving for b and d here. My first step was really just to make both of these things equal the same thing. This red function equals 0, this blue function equals 0. With both of them equaling each other, I can just set both of them equal to each other, where I have log base b of 2 to the 5th power plus d minus 2 is equal to log base b of 8 to the 5th power plus d minus 12. Now in this step here, I'm just going to try and move some terms around. I want to subtract d from this side, and if I subtract d from this side here, both my d's end up going away. So my d term is just gone, right? If I'm adding d over here and I'm adding d over here, let's say d was 100 or some other number, if I'm adding it both on both sides and I subtract it, then that variable just completely goes away. With that one gone, let's start tackling these constants here of that plus 12. Let's move the constant over where I'm just adding 12 to this right side. That 12 cancels out. That 12 and minus 2 turn to 10. Now with my constants on that left side, let's bring that log over this way. Let's subtract that log base b of 2 to the 5th power on both sides. And all these steps here are just basic algebra. We're just subtracting and adding the same thing on both sides of the equation. Now in here, notice what happens. But first, that cancels out. This goes over to here. We know one of these properties. We know what log base b of something minus something is. Really, that's just the quotient of both of those internal terms. We get log base b of 8 over 5 divided by 2 to the 5th power equals 10. Now that I have this set up here, what I want to try and do is now solve out the internal section of this log base b. If I type this into my calculator of 8 to the 5th power divided by 2 to the 5th power, I end up getting like 1,024. With this point here, I now want to try and use our rock and roll method to try and get rid of this log. What I mean to say is, I know that the b raised to the power of 10 is going to equal 1,024. Whatever that base is being raised to the power of 10 to get 1,024. Now with this step, I just need to take the 10th root of both sides. On that left side, 10th root simplifies out, and that right side, I get b equals 2. That was one way to solve for b. I was able to math out about 2 other ways to try and solve for b. I'd love for you to try out your own way. But with this, once you find b, the next step is I just want to plug into one of these equations here to solve for d, where that b now is going to be equivalent to 2, and now I can solve any one of them. Notice that the red one actually has something special about it that makes it the preferable equation to solve for. I'm going to solve both of them at the same time. I want to pause just for a minute. As an educated guess, what about the red equation makes it the preferable equation to solve for? Pause for a moment and think. Do you see it? I'll show you now. For this here, we have both the equations set up. My very first step is to take care of that log base 2 of 2. And whenever we have a log, my first step is to bring that 5 into the thing. That was my bad. Now our next step is to take care of that log base 2 of 2. Notice what happens to those log bases. I'm taking the base of a base. It's the same base. Because it's the same base here, I'm only left with that exponent of 5. I want to do the same thing for the blue equation. I don't want to deal with that 8 to the 5th power. I want to deal with something to the 2nd power raised to something. Now in general, when we have something inside of the log, or just anything in general, that has a power raised to a power, where this is 2 raised to the power of 3 raised to a power of 5, really all we're doing is multiplying that 5 and that 3 to get 2 raised to the power of 15. But instead of going down this route, our log base 2 of 2 just simplifies to that exponent of 5. Now while that equation sits there, we're going to solve this one out the same way. Log base 2 of 2 to the 15th power, that log base of 2, that base of the 2 for the exponent simplify out, and we're left with 15 plus d equals 12, along with that 2 equals 5 plus d. Now all that's left is to subtract 5, to subtract 15 for both sides, and we end up getting d by itself, where d equals negative 3, and d equals negative 3. It's the same solution for both of these equations here, but that red one was a little bit easier for us. I'm curious to know if you guys spotted that little pattern. With d and b solved for, we're able to fully answer out part b, where L of x is equal to 5 times the log base of 2x minus 3. Keep this status in mind when we're taking some unknown log and we're given points to then plug into that log function to then solve for those missing variables in this next example. For example 2, select the values of the logarithmic function g are given in the table below, where g of x is equal to a plus b times log base 3 of x. Part A is the same as that last one, where we want to write 2 equations that can be used to find the values of a and b. Oh, look at that. We're given 2 more points, as if it was serendipitous. We have an x value. We have a g of x value. We can write those 2 equations just like what we did before. We had that first point in red and that first point in blue, but there's something special about that red log function. Instead of us making both of those equations equal each other, where we would add 4 to both sides and subtract 1 to both sides and make those equations equal to each other, notice something special about that log base 3 of 1. I'm going to bring it over here to make it easier to see. Anything with log base of anything to the first power is equivalent to 0. That there equals 0 for us, and we know that since this equals 0, we have now -4 equals a plus b times 0. And anything times 0 is just gone. So we're left with a equaling -4. Way easier solved than the first problem. With a equaling -4, we can plug that -4 in to where g of x for that blue function is to solve out that part b. We now have 1 equals -4 plus b times log base 3 of 9. Now I want to pause here. We do need a second equation to solve for b. If we were to plug in this -4 back into the original equation, since we're still taking the log base 3 of 1, that term will always equal 0. So we'll never be able to find what that variable b would have been even if we plug in a. We can only find this variable of b if and only if we plug that variable of a, being -4, into a second equation that doesn't eradicate or get rid of that unknown. With that said, we're now able to solve out this log of 3 of 9. We're going to do it the same way like we did in that last problem, where we want to manipulate that value of 9 into something that's 3 raised to the power of something. I know you guys know 9 is just 3 squared. And now with log of 3 and base of 3, we can just simplify those out and we're just left with 2. So we know log of 3 squared is just equal to 2. And now we can get rid of that -4, where we add 4 to both sides. And we end up getting +4 + 4. 5 is equal to b times 2. We now just divide by that times 2 to both sides. And we're finally given that b is equal to 5/2. Now for me personally, I do like seeing your fractions as answers. The reason why we enjoy fractions a little bit better than decimals, especially in pre-calculus, is it's easier to graph fractions, and it's nicer to use for slopes and inequalities. Fractions make it a little bit easier than decimals, but I'll digress later. Now that we're given a and b, we're now able to plug those into our g of x, and we're given our final equation of g of x equals -4 plus 5/2 times log base 3 of x. Thank you very much for joining me on this first video for Lesson 14a, where we solved out 2 unknown variables in our log function based off of 2 known points. If you have any questions at all, please leave them in the comments down below, and I look forward to seeing all of you guys in that next video. Take care.